Do you have to keep moving it?
Yeah, unfortunately.
Does it capture at least this entire area?
Yes, it does.
Okay, so you just have to move from here to there.
Yeah.
Okay. Okay, let's see if the mic works. Yeah, is it working? Yeah, it's working. All right. So it's already recording?
Yes.
Okay, thank you. Okay, so good afternoon, everyone. Welcome to the second lecture of matching theory. I'll do a quick recap of what we discussed in the first lecture. Maybe this is better. Right. So we discussed what matchable graphs are, what matching covered graphs are, and we proved this characterization of matching covered graphs. I actually forgot to include connected, I think, in the last lecture. I should have included that. So, right, so it's basically an easy consequence of Tutt's theorem that a connected matchable graph, which means it has a perfect matching, is matching covered, which means every edge belongs to some perfect matching, if and only if every barrier is a stable set. And because in this course we'll mostly be talking about matchable graphs, we will hardly talk about graphs that are not matchable. I mean, there are exceptions. We may talk about hypermatchable graphs, for example. So because we are mostly going to talk about matchable graphs, you can take this as the definition of a barrier. But this is just the same definition that we have in structural graph theory, assuming the graph is matchable. Then it is exactly this. If the graph is not matchable, then the definition of barrier is more general, and then this is not the correct one. Yeah. Okay. Questions, concerns? Everybody is convinced that we proved this corollary? Yeah? Okay, and by stable set, we mean independent set. The set there are no edges in that set, in the graph induced by that set. Okay. So I think I mentioned last time that the main goal for the next couple of lectures, maybe just today, I don't know, is to prove Kotzig's canonical partition theorem. So the theorem says I don't remember the year, it's probably 1950s or 60s. Does anybody remember? If not, it's fine. So the theorem says that for any matching covered graph, in a matching covered graph, the maximal barriers partition its vertex set. Okay. Right. So this is what we will prove today. Hopefully we'll finish it today itself. It's not too difficult, thanks to Lucchesi, Murty, and the people who came before them, who developed a nice theory. So the moment you see a partition, what do you think? There should also be something else, right? The moment you see partition, what else do you expect to see? Underlying almost every partition, there is an equivalence relation. So a natural question that arises is, what is the corresponding equivalence relation? And the answer is basically here. So we want two vertices to belong to a barrier, right? If they belong to the same equivalence class, as per the equivalence relation that we have not yet defined. So now can we define the equivalence relation? We will say that two vertices u and v in a matchable graph. We will allow the definition to have matchable graphs. We will say that two vertices are Kotzig-related if the vertices are u and v. So when should we say that they are Kotzig-related? According to this lemma. This lemma is the hint. Two vertices u and v of a matchable graph G are Kotzig-related if G minus u minus v is not matchable. That is crucial. In fact, when I was preparing my own notes today, I wrote matchable. I realized this is wrong. That's why I always capitalize the not, because it's very easy to miss the not, even when it is written. Kotzig-relation. So I don't know if this term is used in Lucchesi and Murty. I'm not sure, but I'm going to use this term, Kotzig-relation. For a matchable graph, G, two vertices u and v, not necessarily distinct, are Kotzig-related we will use the notation u and v are Kotzig-related with a k on the top. This notation is also probably not used in Lucchesi and Murty. If G minus U minus V is not matchable, okay? So this is the relation. This relation in itself, even for matchable graphs, need not be transitive. It is clearly reflexive. Yeah, G minus U minus V will have odd number of vertices, so therefore it is not matchable. It is clearly symmetric, no doubt about that. The question is it transitive? For a matchable graph, the answer is it need not be transitive. I will leave that as an exercise for you all to think about. Construct examples. Construct examples wherein the Kotzig-relation is not transitive. Yeah. However, in the case of matching covered graphs, we will prove that this is actually an equivalence relation. So that is a consequence of Kotzig's theorem. So in fact, this is one way of, so maybe I'll call it Kotzig's theorem. It will be a corollary of what we will prove. In a matching covered graph, the Kotzig relation is an equivalence relation. Yeah. So this morning, I was thinking that maybe these two are equivalent. I am used to thinking that they are equivalent, but now that I have to teach the course, I have to think more. What I was able to prove is that this implies this, and we will actually prove this therefore it will prove this. What I was not able to convince myself, at least this morning, was that this implies this. Maybe I'm missing something. So DIY, or rather TIY, does the corollary imply the theorem? Right, without actually proving the theorem from scratch. Right, then of course it does imply. So we will prove the theorem, and therefore we will get the corollary as a free thing. And the theorem actually implies the corollary. The above theorem implies Kotzig's theorem. This one. That's not too difficult. Just whatever we are covering today, most likely, is basically from chapter 3 of Lucchesi and Murty. Let me just confirm. Yeah, chapter 3 is called Canonical Partitions. Yeah. So everything today is basically chapter 3. Okay, so the next goal is to prove the canonical partition theorem. In any matching code graph, the maximal barriers partition its vertex set. Yeah. So let's try to think about what it means, what we need to prove. Let's try to figure out something like it suffices to prove the following. Yeah, all good? Let's try to figure out some statement like it suffices to prove the following. Then we will just deal with that statement. Yeah. So let's say G is a matching code graph. And let's take a maximal barrier. B is a maximal barrier. Maximal barrier can't be empty set. Does everybody see why? Maximal barrier cannot be empty set. Empty set is a barrier. Empty set is always a barrier in any matchable graph. But it is not a maximal barrier. Everybody sees that? Yeah? Every singleton is a barrier. If you delete any vertex, you will get exactly one odd component. Right? You can't get more anyways. Graph is matchable. Right? So you will get exactly one odd component. You may get even components. I don't care about those. So every singleton is a barrier. Therefore, empty set is not a maximal barrier. Right? So we'll take a maximal barrier. Therefore, it has vertices. Could be a single vertex. But for the sake of making the drawing interesting, let's put some vertices. So because I'm deleting 5 vertices in this example, by definition of barrier, I shall get 5 odd components. Typically, I will use circle for odd components and a square or rectangle, whatever, for even components, generally speaking. Of course, this is also a rectangle, but that's not the point. Yeah, so I delete these 5 vertices and I get 5 odd components. That's a barrier, right? I would like to claim that it suffices to prove the following statement. I want a statement that takes one vertex in the barrier and takes one vertex outside the barrier. Yeah? Or as Santosh likes, inside barrier, outside barrier lemma. Okay, so we'll take one vertex inside the barrier, one vertex outside the barrier, and I want to make a statement about these two vertices, u and v. And I want to say, if I prove this statement, then by this lemma, we are basically done. It suffices to prove the following statement. Okay, what is the statement? I will take one vertex in the barrier. For any vertex u in the barrier and a vertex v not in the barrier, blah. Fill blah. Think about it. If you think you have an answer, just raise your hand and I'll come and talk to you. Anyone else? Okay. Something strange happens when I. Okay. Anyone else? I mean, if you've already figured it out, you can just raise your hand. Okay.
Does not exist barrier containing u and v.
Okay, that is one way to look at it. But I want to so now can you use the lemma?
G minus u is matchable.
So if you have an answer in terms of barrier, I want you to use the lemma to remove the word barrier, which is what we will actually prove. Okay. So we will prove that G minus U minus V has some property. Think again. Then we want the maximal barriers to partition the vertex side. So, do you want a barrier containing U and V, or do you not want a barrier containing U and V? Of course, if there is a barrier, there is a maximal barrier, by definition of maximality. So, right. So, you want it to partition, so what should you get? Right. You don't want a barrier containing U and V, right? So it should be V minus U minus V should be matchable. That's exactly what we'll do. Yep. Okay. So let's just write it down. And we'll prove that G minus U minus V convince yourself that if you prove this, then by the lemma you are done. It implies that any two barriers, any two maximal barriers are either the same or they are disjoint. And since every vertex belongs to a barrier, therefore to a maximal barrier, it follows that the maximal barriers partition the vertex set. Right? No vertex is left out. Partition means everybody should also be covered, right? Yeah. So I claim that if we prove this, we are done. If you are not convinced, take some time. Right. Work through the argument. Supposing there was another maximal barrier. Supposing there was another maximal barrier that had some intersection with this barrier. So therefore it will contain a common vertex. That will be your view. If it is completely contained in that barrier, well then it's not maximal because B is a maximal barrier. Therefore it also has to contain an element outside. Right? If there is a maximal barrier distinct from B that intersects B, then it has to have an element inside B and it has to have an element outside B.
B is not matchable.
Right? But then that means that G minus U minus V is not matchable for some U inside the barrier and for some V outside the barrier. Yeah? Yeah? This, if you prove this, we are done. Right? That's all we need to do. Everybody with me? Yeah? Okay. So this is what we need. We just need to prove this property. Alright. So what we will do is, we will first look at some properties of barriers and then some properties of maximal barriers, and then we will apply those properties and prove this. These properties are actually very easy. Let's see. So, aside. Okay.
So you are saying that we can cover the whole vertices set by the barriers.
That's right.
Uh,
Maximal barriers.
By the maximal barriers.
That's right.
There we are using the fact that singleton is a barrier.
Yes, we are also using the fact that every vertex is a barrier. Therefore, maximal barriers will not miss out any vertex. That's also important. Yeah? Yeah, maybe I'll just write an observation. Observe that each vertex comprises a barrier. This in particular implies that the set B, in particular, which is a maximal barrier, is not empty. And yeah, because of this observation, if we prove this statement, we are done. Yeah. So properties of barriers. We will look at properties of barriers in a matching covered graph. So let's suppose G is a matching covered graph and B is any barrier in a matching covered graph. Yeah. So first of all, we know that the barrier is stable. We've already proved this. So this we already know. Let's just record it. We know that B is stable. We know that we will have as many odd components as the number of vertices in the barrier by definition of barrier. What about even components? Will we have any even components? Right? Supposing there is an even component. then does everybody see a contradiction to the matching covered property? Either you can see a contradiction to the matching covered property, or you can consider that there has to be some edge like this, and now you can see a contradiction to this property by considering a different barrier. Right? Both of them are valid ways. Yeah? Okay, so in both arguments you will get a contradiction, same thing. So another point to note, in a matching covered graph, for a barrier, you can't have any even components. G minus B has no even components. Right? This is for all barriers. We are not using maximality anywhere. Now I want to make one more observation for maximal barriers. Okay, this observation is also crucial in what we are trying to prove. So now G is a matching covered graph and B is a maximal barrier. We know that all the components are odd components, but now we will use maximality to prove something stronger. Yeah? We know that every component is an odd component. When I put in brackets, I mean that it is implied without my saying it, because we just said it here. Then each component of G minus B has some stronger matching theoretic property. It's an odd component, so it can't be matchable. So what do you think? Hypomatchable. We finally have a graph with odd number of vertices, so we'll go with hypomatchability. Yeah? This turns out to be true. Each odd component of G minus B is hypomatchable. Of course, this needs a proof. I will leave it as a TIY. Right? If you don't get it, we'll discuss further. Basically, you have to use Tutt's theorem. One direction or the other doesn't really matter. Don't really care. So, no, you have to use the difficult direction of Tutt's theorem. Yeah, DIY. Prove using Tutt's. Generally, when people say Tutt's theorem, they can mean many things because Tutt did so many things. In this course, when I say Tutt's theorem, I mean Tutt's perfect matching theorem, also known as Tutt's one-factor theorem. Right? Okay. So, if you prove this, we'll assume this for now. Okay. So, we will use the fact that because we have a maximal barrier, all of these components are not only odd components, they are hypomatchable. They will help us in constructing our desired matching, perfect matching in this graph. Right? Okay. And let's just make more information. We will take some vertex here, and we will take some vertex here, and we want to prove that G minus U minus V is matchable. Right? So hopefully you can see why hypomatchability will help us in some way. But it is not enough, we need more. We need more than the hypomatchability of the odd components. Okay? Okay. So, we will see some more concepts. And this is actually we are going to go towards one of the very important concepts in this entire course called tight cuts. Okay? So you all know what a cut is. You've all done SGT at some level or the other, so you know how important cuts are in life. So in matching covered graphs, special types of cuts play a very important role. And one such type is called tight cuts. So let's see. In this example, you have a barrier, need not even be maximal. Just think of a barrier and the odd components in a matchable graph. Look at this cut. The vertices, the edges going from this component to the rest of the graph. Where will they go? Well, they'll have to go into the barrier because this is a component after deleting this. So look at the edges going from here to the rest of the graph, which means they'll go here. What can you, so I want to think about this cut. Does it have some special property with respect to perfect matchings of the graph? If I take any perfect matching M, and this is my cut C, what can you say about M intersection C?
Greater or equal to 1.
Greater or equal to 1 is definitely true. Can you make it stronger?
Yeah, greater or equal to 2.
You are thinking of the cut itself. You are not thinking of M intersection C. The reason you are saying greater than or equal to 2, I think.
Greater or equal to 3, I think.
No, think again. There are 5 vertices here, and there are 5 odd components. Right? Think carefully. There are 5 vertices, 5 odd components. There could be 100 even components. I don't care about them. What was it?
1.
1. Exactly 1. Yeah. Every perfect matching will meet this cut in exactly one edge. Yeah. Let's make that observation. This is not even about matching covered graphs. This is about matchable graphs. So G is a matchable graph. B is any barrier. Then for every odd component, because now we can have even components, for each odd component, let's say J, M intersection partial of J, for a subgraph J, I will use the notation partial of J as a shorthand for partial of vertex set of J. Yeah. M intersection partial J is equal to 1 for every perfect matching N. Yeah. Everybody agrees? Just follows from definition of barrier and perfect matching and counting. Yeah. Okay. We will call such cuts tight cuts when the graph is matching covered. Typically, we will not talk about tight cuts in matchable graphs, right? So, as far as the definition is concerned, you can probably assume your graph is matching covered. So, such cuts are called tight cuts in matching covered graphs. Does every matching covered graph have a tight cut? Yeah. Why? Singleton. Single vertex, you look at partial, by definition of perfect matching, it is a tight cut. Right? So of course you will have trivial tight cuts. What we will be mostly interested in is non-trivial tight cuts. But the definition of tight cuts allows for trivial tight cuts. Yeah? Yeah, so clearly partial of V is a tight cut for each vertex V, and these are called trivial. This is also what we call a trivial cut in graph theory. When we say trivial cut, we generally mean cut of a single vertex, cut corresponding to single vertex. Sometimes you also say the anti-cut is trivial. But anyways, what is more interesting is non-trivial. So non-trivial means both of the shores should have at least two vertices. Right? Shores of a cut. I hope everybody knows this, right? So if this is a cut, we will call x and x bar the shores of the cut. Yeah. So by non-trivial we mean each shore has at least two vertices. Yeah. And of course non-trivial tight cut means each shore will have at least non-trivial tight cut means each shore will have at least. Can you make it stronger? Intersection with every perfect matching is 1. So what can you say about the number of vertices in the shore? Odd. Right? Yeah. So for non-trivial tight cut, each shore will have at least 3 vertices. Yeah. Okay. So everybody okay with tight cut? So are you all convinced that in this drawing, all of these are tight cuts? You have a matching covered graph, doesn't even have to be matching covered. You could have a matchable graph. B could be any barrier. You look at any odd component, its partial is a tight cut. Yeah, okay. So, what we will do is, for a tight cut, we will get two smaller graphs. Yeah, given any tight cut, we will obtain two smaller graphs. We will argue that those two smaller graphs are also matching covered. And this will be very crucial for the entire course. Yeah. So, can someone tell me, if I have a tight cut in a matching covered graph, supposing this is a tight cut, then can you see a way of getting smaller matching covered graphs?
Remove both the end of the matched edge.
Let's do one example. Here is one of my standard examples. Here is a barrier. Doesn't have to be a barrier, but anyways, this is a barrier. And observe that this is a tight cut, this is a tight cut, this is a tight cut. For this tight cut, can you think of a way to obtain smaller matching covered graphs? For this example, it should work. The fact that it works for all examples is an exercise, not too difficult. In this example, what would you do? So the property you should focus on is every edge belongs to a perfect matching. Don't worry too much about connected. Keep that secondary. When you do this operation, you should get two smaller graphs, and in those smaller graphs, every edge should belong to some perfect matching.
Recall the question again.
So I want to get two smaller matching covered graphs from this matching covered graph by doing some operation related to this tight cut. So this is a tight cut, C. Related to this tight cut, I want to do some operation. the number of vertices should remain even number, and each shore has an odd number of vertices, right? At least 3. So what do you think? Can you think of a operation that would give us smaller matching covered graphs? Contraction. What do you want to contract?
That edge itself.
Oh, you want to contract an edge, but that will make the number of vertices odd, right? So you can't contract an edge, but can you contract something bigger into a very small thing?
Whole.
The whole shore. Take the whole shore and squeeze it into a single vertex. Yeah. Now try to convince yourself that the 2 smaller graphs you get by doing this operation, shrink one shore into single vertex and then shrink the other shore into single vertex, you get 2 graphs, right? What do you get in this example? In this example, let's say I call this x and I call this x bar. What is G shrink x? This is the notation for shrinking the entire set into single vertex. And we will not keep loops because we are in matching theory, right? So we will throw away, it will just become a vertex without any loops. So what will you get in this example? If you shrink x, what graph do you get? K33, yeah? We get K33 in this example. And if I shrink x bar, what do I get? K4. So if I shrink x bar, in this example, I get K4. Yeah? Both of those are matching covered. That is easy to see, right? K33 and K4, very symmetric graphs. You can all see that they are matching covered. Turns out this is always true. You take a matching covered graph, you take a tight cut, you shrink any shore, either shore, you will get a smaller matching covered graph. Smaller if that cut is non-trivial. Right? So, okay, so things to prove. So, let's see. G is a matching covered graph. Partial of x is a tight cut. We did not argue that the 2 graphs are connected. In fact, we did not argue anything, right? We did not prove anything. So you have to prove 2 things, right? So consider these 2 graphs. What is? That's why I don't use this for minus. G shrink x and G shrink x bar. Prove that they are both matching covered. This is an easy DIY. The only difficult part here, if any, is to prove that the 2 graphs are connected. Every edge belongs to perfect matching is really easy. It just follows from definition of tight cut. If you just think about the definition, you will be able to see why every edge belongs to a perfect matching in these 2 graphs. The connected is actually the slightly trickier part. For that, I will give you a step. Prove that every tight cut is a bond. You all know what a bond is from SGT. Minimal non-empty cuts. In a connected graph, a bond is exactly the same as a cut for which both the shores induce connected subgraphs. A cut is a bond if and only if the shores induce connected subgraphs. Right? So this is prove that partial of x is a bond. Yeah, so this is the first thing you prove, and then you prove that the 2 graphs are matching covered. Okay? So we will assume this to be true. We will assume this to be true. And we will proceed to prove this. Okay? We will need one more small observation. Okay. But to motivate that observation, let me try to use this example here. So here I have a barrier. Let's just recap what we are doing, right? We have done a bunch of asides by now. let's come back to our main proof. We are trying to prove Kotzig's canonical partition theorem, right? We took one maximal barrier in a matching covered graph, and we are looking at the odd components, and we observed that it suffices to prove this statement, that for any vertex in the barrier, any vertex outside the barrier, you delete the two vertices, the remaining graph has a perfect matching. If you prove this, we are done. Right? One thing we will find useful is the hypomatchability of the odd components. But that will not be enough, because look, using hypomatchability, I can basically, I want to delete this vertex because I want to get a perfect matching in G minus U minus V. So I can get a perfect matching here that saturates everybody except V. So I can delete V and match the others. I can do the same thing here, but I also have to saturate these vertices, right? Okay. Yeah. So we will need more than just the hypomatchability. The hypomatchability of the odd components is not enough. We need something more. Yeah. Okay. So let me ask you a question. From this figure, can you see how to come up with a bipartite graph? How can you come up with a bipartite graph from this figure? And it is related to what we did for a tight cut. We shrunk a whole set into single vertex. Right? Can you do something similar here and get a bipartite graph? Yeah? Shrink each odd component into a single vertex. If we shrink all the odd components into single vertices, we'll get a bipartite graph. Do you all agree? Remember, there are no even components. This is the whole graph. Right?
There is no edge in between barrier.
Right. Barrier is also, that is another point. The barrier is a stable set. So there are no edges here, and all the edges will just go between this colored class and this colored class. Yeah? Okay. Of course, the shrinking, we will do one step at a time. Supposing I shrink this into single vertex, do I get a matching covered graph? If I shrink this into single vertex, do I get a matching covered graph? Okay, this is a tight cut. After I shrink this into single vertex, now I will shrink this into single vertex. Do I still get a matching covered graph? Yeah? You all agree? Because this is still a barrier, this is still a tight cut. So if I shrink all of these odd components into single vertices, I'll get a matching covered graph. The observation we are using here, there is a more abstract observation we are using here. Maybe I'll define this anyways, right? So for two cuts, we will define a term that we will find very useful later. So if you want to visualize two cuts in a graph simultaneously, partial of x and partial of y, you get this figure. Do you all agree? This figure allows you to visualize two cuts simultaneously. This is my first cut, partial of x, and this is my second cut, partial of y. I get four quadrants. Let's this is x, x bar, y, y, y bar, this quadrant is x intersection y, this is x bar intersection y, this is x bar intersection y bar, and this is x intersection y bar. Given any two cuts in a graph, this figure kind of helps you to visualize both the cuts simultaneously. Now the question is, are these quadrants empty or are any of them non-empty? If all four quadrants are non-empty, we will say that the two cuts are crossing cuts. By crossing cuts we mean all four quadrants have to be non-empty, right? Two cuts, partial of x and partial of y are crossing so G is any graph if all four quadrants x intersection y, x bar intersection y, x intersection y bar and x bar intersection y bar are non-empty. Yeah. If they are not crossing, we will say they are laminar. Otherwise, they are laminar. Yeah. Now let's go back to our example. Let's say this is my partial x, the orange cut in that drawing, and let's say this is my partial y. So think of this as the set x, think of this as the set y. Are these two cuts laminar or crossing in this drawing? So partial x is the cut corresponding to one odd component and partial y is the cut corresponding to another odd component. Are these two cuts crossing or laminar? Laminar. You all agree? Because x intersection y is empty. Yeah. So laminar cuts basically, if two cuts are laminar, you can sort of go to a simpler drawing. They look like this. One of the quadrants is empty. So essentially you can replace this drawing. This drawing is more useful when you don't have any information about the cuts. They could be crossing or laminar. But if you know that they are laminar, which is more well behaved than crossing, then you basically can go to a simpler drawing. Right? Something like here, x and y, they have empty intersection. So x will be basically this side, y will be this side. Observe that x intersection y is empty and the other quadrant is non-empty, could be non-empty, but the fourth quadrant is missing because it is empty. Yeah, okay. So I'll explain why I did this. I don't need all of this complication today, but I want you to get used to some concepts because we will hit those concepts very soon, right? So the point I want to make is, if I have two tight cuts that are laminar, what I can do is, I can shrink one showed here. I want you to observe that in the smaller graph, this cut is still a tight cut. I give you a matching covered graph. Running out of space, as always. This is useless. I want you to make an observation. G is a matching covered graph. Partial x and partial y are tight cuts, are laminar tight cuts. So you can adjust notation so that some quadrant is empty. I will make, this is the x intersection y is empty. Adjust notation so that x intersection y is empty. So the drawing looks like this. Yeah. Now what I can do is I can shrink x into a single vertex. And I want you to observe that partial of y will still be a tight cut in the resulting graph. Then, if I shrink x to single vertex, in the graph G shrink x, this is a matching covered graph by the exercise that is a DIY. Then in this graph, partial of y is a tight cut. Let's make a drawing. So here I am shrinking x to a single vertex, and the remaining set is like this. You'll have some edges like this, I don't know, and this cut is the yellow cut. Y is still a set over here, and x became a single vertex. I will call it little x. Now let's look at the statement. I have a matching covered graph G. I have two cuts, tight cuts. They are laminar. So one of the four quadrants is empty. I can adjust notation so that x intersection y is empty. So the drawing will look like this. Yeah. Now my claim is that when I shrink x to a single vertex, I know I get a matching covered graph. In this matching covered graph, I claim that the original partial of y cut, the same set of edges, is still a tight cut. You need to check that every perfect matching meets the cut in exactly one edge. Yeah? Is everyone convinced? If there was a perfect matching that met the cut in 3 or more edges, then you will have such a perfect matching also in the original graph. For that you should make the other contraction also. One way to see it is draw both the contractions. I only drew one contraction. I only drew one partial x contraction, but there are two of them. If you draw both of them, it's actually very easy to see. Right? So this is actually the observation we are using over here. This observation, I will leave it as a DIY in case you are not fully convinced, but I'll also call it proved. Right? This observation is what we are using here. All of these are laminar cuts. If I shrink this to single vertex, I will get a matching covered graph. Now this is a tight cut. I shrink this to single vertex. This is again a matching covered graph. I keep doing this, so I'll get a bipartite matching covered graph. Okay? Yeah. Of course, I did not have to go through this more general observation. I could have just used the fact that this is a barrier and therefore this is a tight cut, right? But I want you to get used to laminar and crossing because we will see some non-trivial proofs using these concepts, right? Okay? So is everybody convinced that we also get a bipartite matching covered graph by shrinking all of these? So, I want to introduce some terminology. I've already introduced a lot of terminology, some more. Okay, let's see. Maybe I should keep writing here. Can I erase some things? Anyways, it is recorded, right? So I'll erase things here. Okay. Okay, so some more terminology to finish the proof. So now G is a matching covered graph. B is any barrier, need not be maximal. Make a drawing of this. So let's say I have 4 vertices this time. I get 4 odd components. Yeah. So we will define some terminology using the observations we have already made. So when I shrink all of these into single vertices, I will get a bipartite matching code graph. We will call that the core of the graph G with respect to the barrier B. Okay, so core of G with respect to the barrier B. Or if you find this too long, you can call it the B core, where B is your barrier. Yeah. So I'll just make a drawing. The B is as it is. And one advantage of using B is now I can use A for the other set, the other color class. So this set basically becomes this set. Each odd component is shrunken into single vertex. Yeah, and I hope we all are convinced, modulo those DIYs, that this is a matching covered graph. Yeah, okay. So the observation is the core is basically a bipartite matching covered graph. Yeah, okay. Now since we have defined the core, let me also throw in one more term which comes from Santosh's works, which should have been introduced much earlier, but for some reason nobody introduced the term to the best of our knowledge. So what I can do, for each odd component, I can shrink the complement to a single vertex. Do you all agree that that is also matching covered graph? For every odd component, let me first draw the odd components. And what I will do is I will shrink the entire complement into a single vertex. So I'll get some graph like this. Number of edges, I don't know how many. Something like this. Let's do a concrete example.
So these are 4 different graphs.
Yes, 4 different graphs. Yeah. So let me do one example, which is the example I drew earlier. This is my barrier B. And I drew this example earlier. For this graph, this is my graph G. This is my barrier B. I have 3 odd components. What is the core for this graph? Let me make it more interesting. This is not interesting enough. Let me make it a bit more interesting. Okay, now, what is the core of G with respect to B? K33. Core is K33. Now I want to give a name to this, so I'll give the name that we gave in Santosh's paper. We will call them the B fragments. This is called the B core. We will call these the B fragments. These are the B fragments. This is not used in Lucchesi and Murty, to the best of my knowledge, right? But we will find it useful. So what are the B fragments here? What are they isomorphic to? You get how many B fragments? 3. 1, 2 and 3. The first one is K2 with 3 edges. We will call this the theta graph. K2 with 3 edges. We will call this the theta graph. Okay? And what about the other 2 B fragments?
K4.
They are K4. So we get the core is K33 and the B fragments are theta, K4 and K4. Yeah? Observe that all of these are matching covered graphs because we just took tight cut and we kept shrinking short. For the core we did multiple such things, but then it follows from the laminarity. And in the case of B fragments, well, it's just one tight cut, you shrink one short, you get matching covered graph. Yeah? Okay, good. Alright, we are getting there. So, To prove that this graph is matchable, we will take the core, we will use the core, which is a matching covered bipartite graph, and we will use the hypermatchability of the odd components. Okay, these are our two ingredients. Okay, let's write down the ingredients. First one, each odd component is hypermatchable. Yeah. Second one, the core, the B core, is a bipartite matching covered graph. Okay, now I don't know how to complete the proof, so we all will think about it silently and see how to complete the proof, including myself. I know I can complete the proof from here, right? For sure. This is all we need. And we may need some facts about bipartite matching code graphs. Those are in your assignment 5 of STT, if we need such facts. I don't even remember. Okay, from here we should be able to complete the proof. B is maximal variable, yes. Yes, here we need maximality because of this hypermatchable. Not for the second part. Only for this first part we use maximal. Okay, yeah. We need one fact about bipartite matching code graphs from STT assignment 5. Okay, maybe I'll not state that. You all have done STT assignment 5, or you've at least read it, so you know what the questions are. Right, so think about that. Yeah, and if you can't finish the proof, then you know what you need, and then you just go to assignment 5 and check that it is there. Right, so we will also use one fact. Okay. So we are already at 325. I am okay going up to 4. Anybody else has a commitment? At 330. Okay. Okay. Anybody else? Only one commitment? Okay. Is it okay if I just continue and you can see the recording? Okay. Anyways, we will not take too long. I basically want to finish this proof, and I just want to give people some time to think about it. And I also need a break. Yeah. Okay, so we'll meet again in 5-10 minutes. Feel free to take a break. Yeah, and try to finish the proof. You want to pause the recording, or how does it work?
Yeah.
Okay. Yeah. Okay. So we'll come back. Let's finish the proof. Right. So what we need to prove is that G minus U is in the maximal barrier, V is outside the given maximal barrier. We want to show that G minus U minus V is actually matchable. If we prove this, then we have proved Kotzig's theorem, canonical partition theorem. Yeah. Okay. Okay. So let me just erase some things that are not necessary. So let's try to finish this. We want to get a perfect matching. The only two vertices that should be exposed are U and V. Let me circle them. Right? Everything else should be perfectly matched. Yeah. So U should be exposed, V should be exposed, everybody else should be matched. So this is easy, right? If I want to match all the vertices here, I will just take a perfect matching after deleting this vertex of this component. So let's say this component is J. J is a component containing V. Right? So we know that J minus V is matchable because J is hypermatchable. So that will match everybody here except for the vertex V, which is good news. Here we want to leave U exposed. Yeah. Now let's draw the core, right? We want to use the ingredient 2 also somewhere. Hypermatchability of these components is not enough to match up these vertices. And we'll also miss out one vertex from each component. So that's bad news. So we'll draw the core. Let's say the B core. So this is my barrier B. And I will call this A, why not? And this is my B core, let's call this H. H is the B core of G. Yeah. So now let's try to map this information here. So U is the same vertex. This is the same vertex. And this fellow in this B fragment, this is in the J, the B fragment corresponding to J. It corresponds to this vertex. Let me call this little j. Yeah? Let me circle this. So this U corresponds to U and V corresponds to the component containing V, little j. Yeah? What do you think we should do here? We should take some perfect matching of some graph. Which graph should we take a perfect matching of? H minus U minus J. If H minus U minus J has a perfect matching, then we may be able to use that in some way to make progress here. You all see that?
Yeah.
Okay, so the only thing we need, so what we need is H minus U minus J has a perfect matching or is matchable. Yeah? Is this true? That takes us to the fact from SGT. In SGT assignment 5, one of the things you prove is in the bipartite matching covered graph. Note that matching covered means you can delete one white vertex and an adjacent black vertex, and now the remaining graph is a perfect matching. But this turns out to be equivalent to deleting any white vertex and any black vertex. Right? So in a bipartite matching covered graph, you can actually delete any white vertex and any black vertex, and the remaining graph still has a perfect matching, which is stronger property than being matching covered, but they turn out to be equivalent. Right? In theory, it seems stronger. Okay, so this is where we will use SGT assignment 5. This is true because of SGT assignment 5. If I am not mistaken, problem number 2, ear decompositions. Yeah, so in the ear decomposition problem, we first prove some other things and then we go to ear decomposition. So that is where this is used. Okay. So this graph has a perfect matching. Good. Let's draw the perfect matching. I can draw it like this.
Can you just write down that statement?
Ah.
Assignment.
Yeah, so basically it just says, I'll just write it here. In a bipartite matching covered graph, I mean, this is a weaker statement. This is a smaller statement. I don't need the whole statement. HAB h minus little a minus little b is matchable for all little a in A and little b in B. This is from STT assignment 5. Yeah? Yeah. It actually has a statement like, for a bipartite matchable graph, the following are equivalent. One of the equivalents is matching covered if and only if this property. So I've just written that part. Yeah. So here we will use this. So we'll delete u, we will delete little j, and we'll get a perfect matching. Yeah. Everybody with me? Yeah. So my perfect matching looks like this. Why not? Yeah. So now let's map it here. What does it mean here? It means that there is an edge like this, there is an edge like this, edge like this, edge like this. Goes to some vertex here, vertex here, vertex here. So we have matched everybody except for the vertices here. Well, we are done now? Hypermatchable. Because all these odd components are hypermatchable, we can now complete this to perfect matching. Something like this. We are done. So we have proved that for any vertex u in the barrier and v outside the barrier, the graph g minus u minus v has a perfect matching. We crucially use the fact that b is a maximal barrier. If b is not maximal, this statement is not even true. We need b to be a maximal barrier, and the place where we used it, we got this hypermatchability. Hypermatchability is crucial to do what we did. Yeah. Okay. So with that, we are basically done with the proof. Right? We have proved that in any matching covered graph, the maximal barriers partition its vertex set. And now I remind you the DIY is to prove that this theorem that we have already proved implies that the Kotzig-relation is an equivalence relation. Right? So this is proved. And once you just DIY, then you are also done with this. What I do not know is whether the theorem itself, the corollary here, implies the original theorem. That part I was not able to figure out. Maybe it doesn't. Maybe the canonical partition theorem is inherently stronger than saying that the Kotzig-relation is an equivalence relation. That part was not very clear to me. But anyways, we have proved both, right, because of one implication. Okay. So that is our first major result in the theory of matching covered graphs. Right? It gives you a beautiful partition of the vertex set. Of course, this partition could be trivial. It could be that every vertex is a maximal barrier. That happens in some graphs. Let's think about it. Yeah, let's do this. Let's do two examples of the canonical partition theorem. So one example is where every vertex is a maximal barrier. What does that mean? If I tell you that every vertex is a maximal barrier, what does that really mean? Complete graphs are included in that. Yes, complete graphs on even number of vertices, of course, that is what you mean. They have the property that every vertex is a maximal barrier. That is correct. But there are more such graphs. I want you to think about this. If every vertex is a maximal barrier, then what does it mean?
Yeah, hypermatchable.
No.
G minus U is every vertex is.
For every pair u comma v, G minus u minus v is matchable. Right? Those we will call bicritical graphs, because hypermatchable is called factor critical. So motivated by that terminology, we will call this class bicritical. Right? We could have also called it hypo-matchable, but that is not very fun. Right? So we'll call it bicritical. So let's introduce these. This is a very natural class of graphs, which actually plays a very important role in matching theory. So what are bicritical graphs? They are, there's a technicality here. They will require them to be connected. Let's see. Okay, I want to say this. G minus U minus V is matchable for all distinct UV in the vertex set. Yeah? There are two issues. First of all, according to this definition, this graph is also bicritical. Yeah? That I don't like. So I don't want this to happen. But in fact, I'm going to make a stronger statement. I don't even want graphs with two vertices. Okay, and I will explain the reason soon. So we will not allow graphs on two vertices. We will require the graph to have at least 4 vertices. Okay? I will explain this reason very soon. Right? So bicritical graph means the graph has at least 4 vertices. And if you delete any 2 vertices, you get a graph that has a perfect matching. This is much stronger than matching covered. Matching covered just means you delete 2 adjacent vertices, remaining graph is a perfect matching. Here we are saying for any 2 vertices. Okay? Okay. Fine. So in a bicritical graph, it is clear that there are n maximal barriers. Every vertex is a maximal barrier. Bicritical graphs have n maximal barriers. Each vertex is a maximal barrier. Yeah? So now let's ask the opposite question. What is the minimum number of maximal barriers? You all agree that you can't have more than n maximal barriers. The partition of the vertex. Yeah. Right? So maximum number of maximal barriers is a bicritical graph. Now I want to ask you, what is the minimum number of maximal barriers you could have in a matching code graph? Can't be 0 because every vertex is a barrier, so there will be at least one maximal barrier. Can there be one maximal barrier? In fact, I've never asked this question myself. I think I'm asking this for the first time. Can a matching covered graph have only one maximal barrier? No, right? One maximal barrier means that the maximal barrier would be the whole vertex set. Now it is clear, right? If you delete the whole vertex set, how can you get as many odd components as the number of vertices you deleted? The only time that happens is when your graph is null graph. So that is not matching covered because it is not connected. Null graph is disconnected. Matching covered graph has at least 2 vertices. So if you delete 2 vertices, you can't get 2 odd components because you deleted all the vertices. So it is clear that matching covered graph cannot have only one maximal barrier. The minimum number of maximal barriers is at least 2. Yeah. Now let us ask the question, what are those matching covered graphs that have exactly 2 maximal barriers? Exactly 2 maximal barriers. Can you give me one class that has this property? Then we will worry about the characterization. In fact, I don't even know about the characterization. Bipartite. Do you all agree? The bipartite matching covered graph, there are precisely 2 maximal barriers. And what are they? They are the color classes. The 2 color classes are the maximal barriers. Turns out these are the only matching covered graphs with 2 maximal barriers. And I think I see a proof now. Yeah, okay, you can think about it. I think this is not difficult to prove. So I'll just write it. bipartite matching covered graphs are the only matching covered graphs that have precisely two maximal barriers. Yeah, not difficult actually. Think about it. DIY. So, one direction is easy. They have two maximal barriers is clear. The fact that they are the only ones that needs an argument, I'll let you think about it. Yeah. Okay. Now let us contrast. So we observe that the maximal barriers is going to be between 2 and n. 2 means bipartite. N means bicritical. Now let me explain why we need this 4 vertices. If I don't put 4 vertices, then I have this graph K2 up to multiple edges. This will be both bipartite and bicritical. This is both bipartite and bicritical because n is equal to 2. Yeah? This is the reason. I want bipartite and bicritical to be disjoint. Okay? In fact, observe that bicritical graphs must be non-bipartite. With this condition, at least 4 vertices. Bicritical graphs are always non-bipartite. That is another reason to put this at least 4 vertices condition. Otherwise, you will get K2 star. It will be both bipartite and bicritical. That is very annoying. And why it is annoying will become more clear in future lectures. Right? So for this reason, we will put this technical condition. And now it follows that DIY bicritical implies non-bipartite. This is somehow related, or it reminds me at least. What is the only bipartite hypomatchable graph? Hypomatchable means factor critical. What is the only bipartite hypomatchable graph? K1. K1 is the only bipartite hypomatchable graph. Hypomatchable graphs are always non-bipartite except for K1. This somehow reminds me of that. Yeah.
This is an assignment.
Yes.
But even I am thinking that K1 is bipartite.
Yes.
2 partitions are there in K1.
Yeah, that's because we allow 2 colorable. So 2 colorable allows
But
the
it
colors
is
not
one
being used.
colorable, na?
Sorry?
It is one color.
Yeah. But 1 colorable implies 2 colorable, right? K colorable implies K plus 1 colorable. But yeah, of course you can define bipartite graphs to have the both parts should be non-empty. You can impose that definition, but generally it is not imposed. Standard definition of bipartite allows for K1, it also allows for empty graph, right?
Empty graph.
Yeah, you can color the vertices in any colors because there are no edges. Yeah. Okay, so I think we have proved Kotzig theorem and we have seen 2 examples of maximal barriers being equal to 2 and being equal to n. There is an exercise in Lucchesi and Murty that I have never solved and I am now remembering it. So you can have 2 maximal barriers, bipartite matching covered graphs. Can you have 3? The answer is no. It turns out that in the matching covered graph, if you have at least 3 maximal barriers, then you will have at least 4 maximal barriers. I don't know how to prove this, I have not tried it. But yeah, if you are interested, you can try it out. Who knows, I might throw it on one of your assignments. DIY. If a matching covered graph has 3 maximal barriers, then it has at least 4. I don't know why this happens. Probably it's not too difficult, I don't know. Okay, good. So, are there any questions, concerns before we? Yeah, so it's almost close to 4 p.m. So now I'm thinking what to do tomorrow. Should we have a lecture tomorrow or should we skip tomorrow? Let me see. There's a class committee meeting. Yeah, you can stop the recording now. Yeah, thank you.